Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Look at your own hands for a second.
Yeah, seriously.
I mean, obviously, if you are listening to this right now and you're like operating heavy machinery or driving down the highway, keep your eyes on the road.
Please do.
But if you're just sitting there, literally just hold your hands up in front of you, turn them over.
Just really look at them.
Right. Look at the knuckles, the vascular structure, the layers of your skin. I want you to take a slow, deliberate inventory of the atomic machinery you are actually looking at.
It's incredible when you really break it down.
It is, because underneath the dermis, you have this hydroxyapatite matrix, which is basically heavily fortified by calcium, giving your skeletal system its rigid architecture.
Right.
And pumping through those visible veins is this highly complex fluid. And sitting at the absolute dead center of every single hemoglobin ring, the exact thing binding the oxygen that is keeping you conscious right now
Is a single atom of iron.
Exactly, an atom of iron. And forming the foundation of every single living cell in your hand and your entire body, really, is carbon.
The anchor of all biology.
We walk around every day intimately familiar with these materials, in a macro sense. We track our calcium intake, we build bridges out of iron, we know carbon is essential, but we rarely stop to ask, what is the actual physical provenance of the specific atoms residing inside your hand right now?
And that is the ultimate cosmic mystery, honestly. It requires a total radical shift in how you conceptualize your own body.
Because they didn't just pop into existence here on Earth, did they?
No, not at all. Those atoms, like every single atom of calcium, iron, carbon that you're currently using to literally exist, they were not synthesized anywhere near Earth.
Right.
They were forged inside the crushing, extremely hot cores of ancient dying stars. And this happened millions or even billions of years before the localized molecular cloud that became our solar system even started to collapse.
So we are walking, breathing, speaking cosmic graveyard.
That's exactly what we are.
And I want to be clear to you listening, that is not poetry. That is literal empirical fact. The iron oxidizing in your bloodstream right this second was born in the catastrophic final fusion cycles of a massive star that detonated eons ago.
Yeah, the basic mechanics of that, the stellar nucleosynthesis, we've understood that for decades. Mostly thanks to astrophysicists back in the mid-20th century.
Right, the general idea of stars as factories.
Exactly. We know that stars are basically these colossal thermodynamic engines. They spend their whole lives fusing lighter elements into heavier ones just to fight off the relentless inward crush of their own gravity.
There's a gap, right?
A huge gap. There's always been this massive, frustrating bottleneck in our understanding. We know the stars make the heavy atoms, and we know those atoms eventually end up here, locked in the Earth's crust or in your own body.
Right.
But to get from the ultra-hot diffuse exhaust of a dying star all the way to a newly forming protoplanetary disk, those loose atoms have to somehow condense into microscopic solid particles.
Cosmic dust grains.
Cosmic dust grains. These tiny refractory grains are what actually seed the universe with solid matter. So the central mystery we are unpacking today is, well, it's a problem of chemical kinetics.
How does it actually happen?
Right. How do dying stars manufacture that solid dust when the physical environment seems perfectly designed to prevent it from ever happening?
I mean, on the surface, it sounds like a simple transition, right?
Yeah.
Gas expands, gas cools down, gas turns into a solid.
Like water vapor turning to ice.
Exactly. But the mechanics of this phase transition out in the vacuum of space are so fiercely complicated. They contradict standard chemical models so badly that it stumped astrophysicists for half a century.
It really did.
So today we are going deep into that mystery. We're going to look at ancient meteorites older than the sun. We're going to talk about the chaotic, violent winds of dying carbon stars.
And that laboratory simulation.
Oh man, yes. This genuinely insane laboratory simulation that tried to recreate a fading star inside a vacuum chamber. And ultimately, we're going to reveal a completely surprising twist involving the absolute most common element in the universe.
It's a profound problem. And honestly, it completely reshapes how we view the chemical evolution of entire galaxies.
Yeah.
Because to solve this, we can't just look at the final dust grain.
We have to map out the exact molecular pathways.
Exactly. Happening in one of the most hostile environments imaginable. We have to start at the outer edge of a dying star.
Okay, so let's go there. The cosmic chemical factory itself. I want to look at the messy death of a star. Walk us through the physical state of a star when it's, heading towards death. Because this isn't just someone flipping off a light switch.
No. It's a very prolonged, wildly unstable period of structural failure. So, for most of its life, a star is in what we call hydrostatic equilibrium.
Gravity pulling in, fusion pushing out.
You've got it.
Yeah.
Gravity pulls the mass inward, and the thermal pressure from nuclear fusion in the core pushes outward, mostly hydrogen fusing into helium.
Right.
But eventually, the core runs out of hydrogen. It depletes its fuel, so the core contracts and heats up, while the outer layers of the star do the exact opposite.
They expand.
They expand massively. The star transitions into a red giant, and then for certain stars into an asymptotic giant branch star, or an AGB star.
And this is where the elemental composition of the surface starts to get weird, right? Because of those convective dredge-ups.
Yeah, so deep inside, helium is now fusing into carbon and oxygen. And periodically, the star goes through these massive thermal pulses.
Like explosive bursts.
Exactly, explosive bursts of helium fusion right in a shell around the core. And these pulses create huge convective currents. They literally dredge up all that newly synthesized carbon from the deep interior and mix it into the outer atmosphere.
So the outer envelope just gets flooded with carbon.
Completely carbon-rich.
But because the star has expanded so much, the gravity holding onto those outer layers is super weak, right?
Right, and the intense radiation pressure from the core just starts physically blowing the outer layers away.
So this is the stellar wind.
Yes. And we're not talking about a gentle breeze here. These are massive streams of hot plasma and gas being shot outward at tens of kilometers per second.
Okay, let's unpack this for a second, because we need to really visualize the physics of this expanding envelope. As the stellar wind blows outward into the vacuum of space, its volume increases, which means its density plummets and its temperature drops.
Basic thermodynamics.
Right. So you have this reactive plasma cooling into a gas, but the atoms are getting further and further apart. The mean free path, the distance an atom travels before it bumps into another one, is growing exponentially.
And that is the exact theoretical bottleneck. The environment is pure chaos. Temperatures are swinging wildly from thousands of Kelvin down to near absolute zero over this huge spatial gradient.
So my question is, how can anything organized like a solid grain of dust with millions of bonded atoms survive or even form in an environment like that? I mean, density's dropping so fast, atoms should basically never encounter each other.
It seems mathematically impossible.
It does. It sounds like a catastrophic factory breakdown. Like the cooling system's failed, the containment is breached, and raw materials are just being hurled out into the void. It sounds like pure destruction.
Well, if we connect this to the bigger picture, you've just articulated the exact reason why this baffled people for 50 years. The old models just couldn't make the math work.
Because it's too hot inside, too empty outside.
Precisely. In a stable star, it's too hot. Any molecule it manages to form is instantly ripped apart by thermal energy. And in the deep interstellar medium, the temperature is fine, but it's way too empty.
The atoms just ghost right past each other.
Right. So the only place this can happen is in this highly specific, highly transient Goldilocks zone within that expanding stellar wind.
Goldilocks zone?
Yeah, there's a specific distance from the dying star where the temperature drops just below the condensation point of these materials, around 1500 Kelvin.
Okay.
And at that exact spot, the density, while low, is still just barely high enough for atoms to collide and bond.
So it's literally a race against time in density. The heavy elements have this incredibly brief window to find each other, bond, and build a solid structure before the expansion of the wind pulls them apart forever.
Exactly. It's a mad dash. And once they do manage to form those solid macroscopic grains, these tiny titans of the cosmos, they completely alter the physical evolution of the entire universe.
Which is wild to think about.
We really need to look at the massive resume of cosmic dust, because without it, the universe would just be a diffuse, dark soup of gas.
Let's talk about that, because when you and I talk about space, it's so easy to focus on the heavy hitters, right? Supermassive black holes, supernovas, gravity. We usually just dismiss a microscopic speck of carbon as like irrelevant background debris.
Most people do.
But cosmic dust is essentially the scaffolding of the universe. Like, you literally cannot build a new star without it, can you?
No, you literally cannot. It all comes down to something called the gene's mass.
The critical mass for a gas cloud to collapse.
Exactly. So, As gravity starts pulling a massive cloud of hydrogen gas together to form a star, the gas gets compressed. And just like any gas being compressed, it heats up. The internal thermal energy spikes.
And heat means outward thermal pressure.
Right, so the gas cloud hits a thermodynamic wall. The outward thermal pressure from the heat eventually equals the inward pull of gravity.
So it just stops collapsing.
It reaches hydrostatic equilibrium way before it ever gets dense enough to start nuclear fusion. To keep collapsing, that cloud desperately needs a way to bleed off that internal heat.
It needs a coolant.
It needs a universal coolant.
But hydrogen and helium atoms, which are, 98% of the cloud, they are terrible at radiating heat away at those low temperatures.
They're awful at it. They don't have the quantum mechanical vibrational modes needed to emit infrared radiation efficiently.
So here comes the dust.
Here comes the dust. These microscopic refractory grains are mixed evenly throughout the gas cloud. And because they are complex, solid crystal structures, they have basically infinite vibrational modes.
Oh, wow. Okay.
So when a hot hydrogen atom bounces off a dust grain, the grain absorbs that kinetic energy. It heats up. And because it's a solid, it acts as an incredibly efficient blackbody radiator.
Meaning it just radiates that heat away as far infrared light.
Exactly. The infrared light just shoots out, escaping the cloud entirely.
So the dust acts as a galactic heat sink. It literally bleeds the kinetic energy out of the gas, dropping the pressure and letting gravity resume its crushing work until the core finally ignites into a star.
It's the ultimate cosmic recycling program. The ashes of dead stars provide the cooling mechanism required to birth the next generation of stars.
That is just beautifully elegant. But the dust job doesn't end there, right?
Not at all. Once that new star ignites, the dust sticks around to build the planetary architecture.
The protoplanetary disks.
Right. Conservation of angular momentum means a lot of that surrounding material collapses into a swirling, flattened halo around the new star. And inside this disk, the dust grains begin the aggregation process.
Which is another kinetic hurdle. Because these grains are microscopic, they don't have enough mass for their own gravity to pull them together.
No, gravity is negligible at that scale.
And if two dust grains smash into each other at high speeds, they just shatter.
Right. The initial aggregation in those disks relies completely on low-velocity collisions and electrostatic forces.
Van der Waals forces.
Yes. When these tiny grains drift into each other very slowly, those weak intermolecular forces are enough to make them stick together. They form these highly porous, fluffy fractal aggregates.
So microscopic grains stick together to form like millimeter-sized clumps.
Yep.
And then clumps collide to form pebbles, pebbles into boulders, and eventually they cross a mass threshold where actual gravity takes over, pulling in material fast enough to form rocky planets like Earth.
But before they even get incorporated into a planet, we have to look at the biological angle, the chemical complexity happening on the surface of these grains in deep space.
Right, because out in the deep interstellar medium, complex chemistry is incredibly hard to achieve.
Because the density is so low. But a dust grain acts as a physical catalytic surface. It's a localized meeting ground.
So atoms freeze onto the grain.
Exactly. Atoms of carbon, oxygen, nitrogen, they freeze out onto the icy mantles of these dust grains. And because they are pinned to a solid surface, they are forced into close proximity.
They have no choice but to hang out together.
Right. And then when a cosmic ray or a high-energy UV photon strikes the grain, it provides the activation energy needed to break simple bonds, allowing those atoms to rearrange into highly complex organic molecules.
We're talking polycyclic aromatic hydrocarbons, simple sugars, amino acid precursors?
Yes, and because these fragile organics are embedded in the ice on a solid grain, they're shielded from the destructive radiation of space.
So the dust is essentially acting as an armored transport vehicle, carrying the required chemistry for life across the cold vacuum of space, potentially delivering it right to early Earth.
Exactly. So when we ask how dying stars make dust, we are really asking how the universe builds the scaffolding for planets and the chemical baseline for biology itself.
Which means we really, really need to know how they're made.
We do. And to figure that out, scientists first had to prove they actually existed in the exact format we thought they did. Which brings us to a crucial piece of physical evidence.
The meteorites.
We had to look at ancient meteorites.
Right, because we can't exactly fly a probe into a dying star 5,000 light years away to grab a sample.
That would be a bit difficult, yeah.
If we want to study stellar exhaust, we basically have to wait for the stellar exhaust to literally crash into our own planet.
And for decades, cosmochemists have been deeply interested in primitive meteorites. Specifically, carbonaceous chondrites.
Like the Murchison meteorite.
Exactly. The Murchison meteorite that fell in Australia back in 1969. These meteorites are basically pristine, unaltered rubble left over from the very formation of the solar system.
They were never part of a planet, so they never melted.
Right. They preserve the original chemistry of the solar nebula perfectly.
But finding stellar dust inside a meteorite isn't like cracking open a geode and looking at the crystals. You are looking for a microscopic needle in a literal pile of extraterrestrial rock.
The methodology is actually quite brutal. Cosmochemists essentially use severe chemical maceration.
Maceration.
Yeah, they take samples of these primitive meteorites and just dissolve them in a succession of highly corrosive acids.
We're talking hydrofluoric acid, hydrochloric acid.
Oh yeah, nasty stuff. This dissolves away all the standard silicates, all the normal rock, all the organic material.
You essentially burn down the entire haystack just to see what survives the fire.
That's a great way to put it. And what survives in that microscopic acid-resistant residue are these incredibly resilient, highly refractory grains of exotic materials.
And the specific material we are focusing on today is silicon carbide.
Ceramics.
No, silicon carbide is something we actually manufacture synthetically here on Earth, right? Like carborundum.
Used in industrial abrasives, ceramics, yeah.
Right. It's super hard. But the grains found in these meteorites are fundamentally different from anything synthesized on Earth, or even anything formed locally in the solar system.
The proof is in the isotopic ratios. When researchers take these microscopic grains and run them through a secondary ion mass spectrometer.
Wait, a secondary ion mass spectrometer. So they aren't just looking at the elements, they are looking at the specific isotopes.
Exactly. Variations of carbon and silicon atoms that have different numbers of neutrons, like carbon-12 versus carbon-13.
Got it.
On Earth and throughout the entire solar system. The ratio of carbon-12 to carbon-13 is incredibly uniform. It's heavily biased toward carbon-12.
Okay.
But when they analyze these specific silicon carbide grains pulled from the meteorites, the isotopic ratios were wildly anomalous.
Yeah.
They contain massive enrichments of carbon-13 and specific isotopes of silicon that just cannot be produced by the standard chemical processes of a protoplanetary disk.
Mind-blowing fact time. Those specific isotopic signatures can only be produced by the slow neutron capture process, the S process, which happens deep inside the core of an actively pulsing AGB star.
Precisely. The isotopic signature is an undeniable physical fingerprint of stellar nucleosynthesis. It was absolute proof that these specific grains are pre-solar.
They are literally physically older than our solar system itself.
Older than the sun.
That is just incredible. You can hold a literal physical remnant of a dead star in your hands. They condensed in the expanding wind, drifted through space for eons, survived the violent collapse of our solar nebula, got embedded in an asteroid, and fell to Earth.
It's a hell of a journey.
So, okay. The meteorites proved the dust exists. The isotopic ratios proved exactly what kind of stars manufactured them. So, case closed, right? We know what they are and where they came from.
You'd think so, but no. This is where the astrophysics community hit a massive, decades-long roadblock. Because while the meteorites proved the what, the observational astronomy couldn't explain the how.
The scientific frustration, the discrepancy.
Exactly. There was a huge mismatch between theoretical models and spectroscopic observations. Traditional models of astrochemical kinetics just assumed a very straightforward mechanism.
They assumed that under the extreme conditions of a dying star, silicon and carbon would just naturally bump into each other and combine.
Right. They look at the dropping temperature and density and assume gaseous silicon and gaseous carbon atoms simply collided, underwent a radiative association, and directly bonded to form silicon carbide molecules, which then rapidly built up into solid grains.
A completely direct two-body collision, A plus B equals C.
That was the standard assumption. But when astronomers actually pointed their infrared and radio telescopes at actively dying AGB stars to watch this process happen in space,
the observational data simply did not match the theoretical prediction.
At all. The expected spectral signatures of direct C-from molecular formation were completely missing.
So just to clarify for the listener, telescopes don't take high-resolution macro photos of individual molecules. They capture spectra.
Right. They look at the specific wavelengths of light being absorbed or emitted by the gas.
And if direct association of psi and C was the primary mechanism, the telescope should have detected a massive, unambiguous signature of those specific bonds forming.
But instead, the spectra were messy. Highly complex, intermediate molecular signatures that the theoretical models just couldn't account for. The models predicted a clean reaction, but the actual cross-section for a direct bond between silicon and carbon is actually quite small. The thermodynamics just didn't support the assumed pathway.
Okay, let's unpack this. So the math said one thing. The meteorites absolutely proved the dust exists. But when we look through the telescopes, the actual process happening in space didn't line up. Something was missing in our recipe.
Exactly. The community knew they were missing a vital catalytic step. But the problem with observational astronomy is that you can't manipulate the variables.
You can't pause the stellar wind, inject a tracer gas, and see what happens.
You're just a passive observer, collecting photons that have been traveling for thousands of years.
So, since we can't fly a probe into a fading star to see what's wrong with our recipe, scientists had to figure out a way to bring the fading star down to Earth.
And this represents one of the most sophisticated feats of experimental physical chemistry of the 21st century. The sheer ambition of this breakthrough is staggering.
Replicating the atmosphere of a dying star.
Inside a laboratory, it's extraordinarily difficult because you are fighting the natural state of matter at every turn. You have low pressures, high reactivity, extreme heat.
Walk us through the methodology here, because, you can't just put silicon and carbon powder into a bell jar, heat it up, and watch it turn into cosmic dust.
No, you have to recreate the exact thermodynamic gradient of the stellar envelope. You need extremely high temperatures to vaporize the precursors into a plasma state, and then you need to rapidly expand and cool that plasma into a deep vacuum to simulate the outward wind.
Okay.
So the researchers used an incredibly advanced vacuum apparatus equipped with laser ablation.
Laser ablation?
Yeah, they started with solid targets of pure silicon and pure carbon, and they fired intense high-energy pulsed lasers directly at these solid targets inside the high vacuum chamber.
So the laser essentially violently rips the atoms apart, creating a highly energetic, localized plasma plume of vaporized silicon and carbon atoms.
Exactly. It perfectly replicates the state of the heavy elements as they are dredged up from the stellar core.
Yeah.
And as this ultra-hot plasma plume expands outward away from the target into the surrounding vacuum, it rapidly cools and drops in density.
It's literally a miniature, localized stellar wind, like trying to recreate a hurricane inside a shoebox, but at the atomic level.
That's a perfect analogy. But creating the wind is only half the battle. You have to monitor the chemistry in real time as the plasma cools.
Right. How do you map atomic reactions happening in microseconds inside a vacuum chamber?
They utilized highly specialized time-of-flight mass spectrometry, coupled with tunable vacuum ultraviolet photonization.
Wow. Okay, that's a mouthful.
It is, but it's a phenomenally precise tool. As the vaporized atoms expand and interact, they use a secondary precisely tuned ultraviolet laser to ionize the newly formed molecules without breaking them apart.
Oh, clever.
And then the mass spectrometer measures the exact mass-to-charge ratio of every single transient molecule that forms in the plume.
So they aren't just looking at the final solid dust grain, they are literally watching molecules dance in real time. They can watch carbon bond to carbon, watch silicon approach, track the intermediate step.
Exactly. It's a real-time molecular tracking system.
Right.
But they didn't just fire the lasers and record the data. They already knew from the telescope data that the direct A plus B recipe was flawed.
Right.
So they ran the simulation under heavily controlled conditions, varying the introduction of one specific, highly controlled element.
The secret ingredient control, hydrogen.
Hydrogen. They introduced carefully controlled concentrations of molecular hydrogen gas into the chamber to see how it interacted with the cooling plasma.
Okay, the stage is set, the instruments are on. What did they find that flipped decades of astrophysics on its head? Let's start with the control group.
Right, the first major finding. When hydrogen was completely absent from the chamber, the control group basically completely validated the telescope observations and crushed the old theoretical models.
The silicon and carbon struggled.
They struggled hard. Even though the temperature and density were in that optimal Goldilocks zone, the mass spectrometer showed that direct reactions between silicon and carbon were incredibly inefficient.
They couldn't organize into the pathways needed to efficiently make dust. The old theories that they just bumped together were definitively proven wrong.
They were bouncing off each other, basically, lacking the necessary pathways to dissipate kinetic energy and form stable bonds.
But then the hydrogen reveal.
The introduction of hydrogen caused an immediate, massive paradigm shift in the chemical kinetics.
Walk us through the step-by-step pathway, because this isn't just hydrogen sitting in the background.
No, it violently alters the chemistry. Step 1. As the plasma begins to cool, the highly reactive atomic carbon interacts heavily with the introduced hydrogen.
Okay.
The hydrogen basically lowers the activation energy required for the carbon atoms to bond with one another. It allows them to quickly assemble into complex hydrocarbons. Specifically, the data showed a massive spike in the formation of acetylene.
Acetylene, C2H2, a linear molecule with a triple bond between two carbon atoms flanked by two hydrogens.
Exactly. It's extremely thermodynamically stable. Acetylene becomes this stable molecular sink for the carbon gas.
So the hydrogen acts as an enabler, forcing carbon into this specific structure.
Right. Now, step 2. The silicon atoms, which previously refused to bond efficiently with bare carbon, have a completely different reaction when they encounter an acetylene molecule.
The acetylene acts as a reactive bridge.
Yes. The mass spectrometer tracked this perfectly. The gaseous silicon atoms aggressively attack the acetylene molecules. Through a series of fast chemical steps, the silicon atom displaces the hydrogen, bonding tightly with the two carbon atoms.
And the hydrogen is just ejected back into the gas phase.
Ejected back out. And the resulting molecule that emerges is a crucial precursor, CaC2.
One silicon atom double bonded to two carbon atoms in a triangular ring structure.
CaC2. This specific molecule is the kinetic key. Once the hydrogen-catalyzed pathways flood the gas with CaC2 molecules, the thermodynamics suddenly favor rapid nucleation.
They start aggregating.
Yes. These precursors easily cluster together to finally build the solid, macroscopic crystalline lattice of a silicon carbide dust grain.
Here's where it gets really interesting. And honestly, it highlights a bit of an irony in early astrochemical modeling. Hydrogen is literally the most abundant element in the entire universe.
Roughly 75% of all normal matter.
Right. It was always there. It's the fuel that powers the stars. The expanding envelope of a dying star is absolutely saturated with it. But for decades, scientists thought it was just the background wallpaper of space.
They assumed that because hydrogen doesn't ultimately end up in the final solid dust grain, it played no role. They thought it was just the empty air in the room.
What's fascinating here is that hydrogen isn't just a passive background gas. It acts as an active, vital catalyst. It actively shapes the chemistry of dying stars.
It's the perfect definition of a catalyst. It lowers the activation barrier, orchestrates the entire reaction, and then exits the system physically unaltered.
Without hydrogen temporarily stepping in to build that acetylene bridge, the carbon and silicon would just remain disorganized, diffuse gases.
Exactly. The efficient production of cosmic dust would just plummet. It fundamentally rewrites our baseline models. We have to view solid matter synthesis as a complex, multi-step catalytic network driven by hydrogen.
Okay, so we've solved the chemical recipe in the lab. Now, how does this change how we look at the actual night sky right now? Does this vindicate the telescopes?
Oh, completely. It resolves the massive spectroscopy problem perfectly. When theoretical astrophysicists took this newly discovered hydrogen-catalyzed pathway.
The kinetic rates for acetylene and silicon forming CC2?
Right. When they plugged those new parameters back into their computational models of stellar winds, the simulated spectra perfectly matched the actual real-world data coming from the telescopes.
The observational data was never wrong.
Never. The models were just too simplistic to understand the chemical reality. Those messy chemical signatures astronomers had seen for decades were exactly the spectroscopic fingerprints of the intermediate hydrocarbons and the CC2 precursors.
And the timing of this breakthrough is incredibly fortuitous, right? Because astronomy is entering a golden age of observation.
The James Webb era.
Let's talk about the James Webb Space Telescope, or JWST. Because unlike Hubble, which looked mostly at the visible and near ultraviolet spectrum, JWST is fundamentally an infrared observatory.
Which is crucial when you're studying stellar dust.
Why is that?
Because of how light interacts with matter. Visible light undergoes severe scattering when it hits a cloud of cosmic dust. The wavelengths are so short they just bounce off the physical grains.
Right, which is why dense molecular clouds just look like pitch-black voids to optical telescopes.
Exactly. But infrared light has a much longer wavelength. It can penetrate and pass right through those dense dust clouds without scattering.
But more importantly for this discovery, infrared spectroscopy is the ultimate tool for chemical identification.
Molecules are always moving. Their chemical bonds constantly vibrate, rotate, and stretch. And the energy of those specific vibrations corresponds precisely to the infrared portion of the electromagnetic spectrum.
So a specific molecular bond, like the double bond between carbon and silicon in our CaC2 precursor, will absorb and emit a very specific, unique frequency of infrared light.
It acts as a definitive optical fingerprint. And JWST is equipped with the mid-infrared instrument, or MIR-I. MIR-I is so sensitive that it can look at the chaotic envelope of a dying carbon star across immense cosmic distances and detect the specific vibrational signatures of these exact intermediate molecules.
But the crucial point is that without this laboratory breakthrough, JWST could have gathered all this immaculate infrared data, and scientists wouldn't have possessed the proper chemical context to interpret it.
Right. We would have seen the emission lines, but struggled to map them. Now we have the correct translation matrix. We know exactly which precursor molecules to look for.
We are essentially putting on a new pair of glasses that brings the chemistry of the universe into sharp focus. We can watch the hydrogen catalyze the carbon, map the density of the precursors, and watch the exact transition zone where they nucleate into solid dust.
We are peering directly into the galactic forge.
Which naturally leads us to pull all these threads together. From a lab experiment in a vacuum chamber, to the massive mirrors of the JWST, to the entire life cycle of the galaxy itself.
The Grand Cosmic Recycling Program.
Let's lay out this vast cosmic life cycle.
It starts in the deep freeze of the interstellar media. Vast, diffuse molecular clouds of primordial hydrogen and helium. Over millions of years, gravity starts to collapse a localized region.
Gas forms stars.
Right. And as we discussed, gravity needs the dust to radiate away the heat so the cloud can collapse. A protostar ignites.
Then stars manufacture heavier elements via fusion.
For billions of years, it acts as a localized nucleosynthetic factory, fusing hydrogen into carbon, oxygen, silicon.
Then stars die and eject enriched material.
The stellar wind carries those elements outward, and the primordial hydrogen aggressively forces the carbon and silicon to bond, manufacturing solid refractory dust grains.
And finally, that material forms future stars and planets.
Those ejected grains drift for eons, eventually getting caught in a new molecular cloud, acting as coolants to birth a new star, and getting trapped in the protoplanetary disk.
Dust is the essential bridge connecting every single stage. It is the literal physical bridge between stellar death and planetary birth.
But we also have to drive the conversation toward the origins of life, because the cycle dictates more than just geological structure.
The origin of complexity.
In the deep vacuum of a molecular cloud, the temperature is like 10 Kelvin. The gas phase chemistry is way too sparse to build anything complex. The probability of 4 atoms colliding simultaneously to form an organic molecule is statistically 0.
But these interstellar dust grains act as microscopic reaction surfaces.
The grain acts as a chemical cryogenic trap. Atoms freeze out onto the icy mantle. Because they are physically localized on a solid substrate, they interact.
And when external energy hits them, like a cosmic ray, they violently recombine into vastly more complex structures.
It's on the surface of these grains that incredibly complicated molecules assemble, precursors to nucleobases, amino acids, biological molecules.
Which brings up the massive unanswered question.
We still don't know exactly how far chemical complexity progressed in deep space before life emerged on Earth.
Did the dust just deliver the raw materials, or did it deliver highly structured, almost fully assembled biological precursors directly into the primordial oceans?
In understanding the exact kinetics of this dust formation is the absolute key to unlocking that answer. We can't know the availability of those organics without knowing how the dust grain itself was built.
When you really synthesize the emotional and philosophical weight of this discovery, it is a profound realization. Think about hydrogen. The simplest element, born mere moments after the Big Bang over 13.8 billion years ago.
The oldest substance in the cosmos.
And it is quietly pulling the strings. It isn't just static fuel. It is actively orchestrating the thermodynamic evolution of the universe. It orchestrates the creation of the dust that becomes rocky worlds, oceans, and ultimately living systems.
Without hydrogen acting as that crucial kinetic bridge, the heavy elements would just disperse into a diffuse gas. Star formation would stall. There would be no solid material to build planets.
No localized surfaces to pre-assemble the organic building blocks of biology.
The macro-scale architecture of reality is entirely dependent on the microscale kinetic efficiency of a single hydrogen atom, catalyzing a reaction in stellar exhaust.
Which brings this entire exploration full circle, bringing it back to you, the listener. At the very beginning, I asked you to look at the physical structures of your own hands.
To consider your own atomic composition.
Every grain of sand you've ever touched on a beach, every asteroid drifting in space, every rocky planet in the habitable zone of a distant star, they all exist because of this exact mechanism of cosmic renewal.
The destruction of massive stars is actually construction on a galactic scale.
And we want to leave you with a final provocative thought to ponder.
The universe spent billions of years transforming simple Big Bang particles into stellar dust. And then it spent billions more transforming that dust into planets, chemistry, biology, and eventually consciousness.
Understanding how a dying star makes a single grain of dust isn't just some esoteric astronomy problem.
No, it is the ultimate attempt to understand the origin story of matter itself. It's the story of how the universe, after billions of years of silent recycling, eventually grew eyes to look back up at the very stars from which it was born.